Right. Well, Alex, thank you for your introduction and also for the invitation to be the token foreigner at this symposium. Kind of makes all that queuing at US immigration seem worthwhile. Okay, I'm very pleased to be here today to talk about the work that we've been doing looking at microscale FAIMS systems combined with mass spectrometry in pharmaceutical analysis. And we know from the first two presentations this morning that ion mobility spectrometry is about the rapid separation of gas phase ions as a result of differences in their mobility in the presence of an electric field and a buffer gas. The complicating factor, as Alex has alluded to, is there are different forms of ion mobility spectrometry. And this morning we're concerned particularly with two of those. The first is the drift tube ion mobility techniques of the sort represented by the first two presentations this morning. And the others are the ones known as field asymmetric waveform ion mobility spectrometry, or FAIMS, which is also known as differential mobility spectrometry. Just to confuse things, they've got two or more names. I'm going to be concentrating on field asymmetric waveform ion mobility spectrometry this morning, and Alex has asked if I would act as warm-up man for what was going to be two presentations, is now going to be his presentation, by saying something about the FAIMS technique to start with. Looking around this hall here, it seems to me that actually quite a lot of you know even more about FAIMS than I do. But just in case you're watching this as a webcast sometime in sort of 2014, you might find this brief introduction useful. Okay, so far this morning we've talked about drift tube techniques, and the critical thing about a drift tube technique is that if you take an ion and subject it to an electric field in the presence of a buffer gas, the ion is going to be accelerated by the electric field, and the velocity that it gains is proportional to the electric field E. So V is proportional to E, and the constant proportionality K is called the ion mobility, and that's a fundamental constant at a particular buffer gas at a particular temperature. And the complicating thing about this is that this holds only under certain conditions, and the key condition is that this relationship only holds when the electric field is under what's called low field conditions. That is to say, when it tends towards zero. In practice, we're talking about operations in the region between 1 and 2 Townsend, and certainly less than about 10 Townsend. The reason why we have to operate in that region in drift tube ion mobility spectrometry is because if we increase our electric field gradient and move that up, then this relationship falls apart and we get deviations from that. And that's shown quite nicely, I think, in this graph here, which goes back to work of Purvis and Guerveront back in 1999. And what we're plotting here is the ratio between the mobility of an ion under some low field conditions and under some alternative high field conditions. So if the mobility is independent of the field, we'd expect the ratio between the low field and the high field mobility to be exactly the same. It's going to be 1. And that is exactly what happens near the origin here. We see that there's no difference between low field and high field mobility. But as we increase the field strength, we begin to see deviations, which may be positive ones. High field mobility is greater than low field mobility, type A ions, or negative deviations, type C ions, or a more complicated process, and they're called type B ions. The relationship is defined by this simplified equation up here, and the important thing is we have an alpha coefficient along here, which is effectively compound dependent. So if we were to look at the difference in mobility somewhere here in the origin and somewhere out here under high field strengths, then that will be associated with the alpha coefficient, and we have the potential to separate compounds on the basis of their difference in ion mobility under low field and high field conditions rather than on their absolute mobility. And that's the basis of the FAIMS or differential mobility technique. How do we do this experimentally? Well, we need a couple of electrodes as shown here on the side, and between those electrodes we're going to transport our ions in a flow of buffer gas. So they're going to be transported through the electrodes along here. We apply to those electrodes this field asymmetric waveform. It's shown on the bottom left-hand side of the side along here, and I'm not going to go into great detail about that. Suffice it to say that the waveform is designed to do two things. First is it's going to initially accelerate our ion towards one electrode under high field conditions, and then at some later point in time it's going to reverse the field. It's going to accelerate the ion towards the upper electrode under low field conditions. So in this case, high field movement is downwards towards low electrode, low field is towards the upper electrode. And the waveform is arranged so that the ion will oscillate up and down between the electrodes and be transported in the buffer gas through the electrodes and be detected. But that only happens if the ion trajectory is such that it's defined by there being no difference in the mobility of an ion under low and high field conditions. So if there's no difference in mobility, then an ion zigzags up and down and will be transported through the device. If there is a difference in mobility between the two, then the ion is going to travel slightly further towards one electrode under high field conditions or low field conditions. The result is that the ion is going to begin to drift towards one of the electrodes. In this particular case here, the upper trace shows an ion which is gradually drifting towards the upper electrode because it has a greater mobility in the low field conditions than it does in the high field conditions. And of course it will be lost under those circumstances. So the second thing we have to do is we have to correct for that. We apply what's known as a compensation field or compensation voltage, which is superimposed on the intervention waveform, which you call the dispersion voltage. And what effectively that does is to correct for this drift to pull the ion down so that it passes through the electrodes. So by applying the appropriate compensation voltage or compensation field, we can arrange for ions which have a differential mobility under low and high field conditions to pass through the detector. And so a field asymmetric waveform ion mobility spectrum is going to be a plot of the compensation voltage or field down here against the intensity of the ions reaching the detector. And in the case of this example, this is protonated reserpine generated by electrospray ionization. We see there's a point around about 1 to 2 Townsend where the protonated reserpine is transmitted through the device because we've used a compensation voltage or field that compensates for the difference in the mobility under high field and low field conditions. And in the perfect world, every molecule, every ion would have a characteristic compensation field for its transmission and could be separated from all others. Sadly, it doesn't work quite like that. Up there in our glorious Loughborough logo pink, I've put a note in to remind myself to emphasize the point that the compensation field for transmission of a particular ion, such as reserpine here, depends or varies with the dispersion field. So when we're doing FAIMS experiments, we need to manipulate both the dispersion field and the compensation field in order to achieve the optimum separation system. Well, that's the basic principles of the operation. In our laboratory, we have 2 devices, and they're characterized by difference in electrode geometry, as indeed is FAIMS and DMS in general. One of those devices, characterized by the Thermo Fisher Scientific one, has 2 electrodes which are effectively concentric cylinders indicated along here. So that the ions from our ion source, in this case electrospray, pass around the annulus between the inner and the outer electrodes where the asymmetric waveform is applied, and they undergo their ion mobility or FAIMS separation there, and ions which traverse the electrodes will exit at this end along here to a detector, or in this case a mass spectrometer. So these cylindrical electrode devices, the electrode gap perhaps around about 2 to 3 millimeters and a few centimeters across the whole device. The other approach on electrode geometry which you can use are ones where the electrodes are parallel to each other. And that's exemplified by the other system we have, which is the Owlstone miniaturized chip-based device. So on the left-hand side of the screen, we can see the chip-based FAIMS device. And here we have parallel electrodes. In fact, we have 16 pairs of parallel electrodes along here. So an ion swarm is generated outside here in the auditorium and will pass through the device into the screen for the FAIMS separation there. And so each electrode pair acts as a separate ion mobility spectrometer, which has an electrode gap of 100 microns. That's between each pair of electrodes along here, where the white is, that's the 100 micron gap. The ions pass down and along the FAIMS device, and in these devices, that's 700 microns long. As I said, there are 16 pairs of parallel ion mobility FAIMS spectrometers here, so that a swarm of ions passing into this device will be separated by FAIMS. The device in our applications I'm going to show is located in our mass spectrometer, which is a time-flight mass spectrometer. It's located just here, just ahead of the inlet capillary for the TOF analyzer, and between the TOF analyzer and the electrospray source here. So ions generated in the electrospray source can be separated by FAIMS prior to introduction into the mass spectrometer. Let me just show you briefly what that looks like experimentally. The chip here, this gives you this idea of the size of the chip. The size of the working part is 4 square millimeters in here, scaled against the finger. That chip on the top left-hand side is enclosed in a casing, a cartridge on the bottom left. That's introduced behind the spray shield of the mass spectrometer and ahead of the inlet capillary in there. And when you close the door on that, on the bottom right-hand side, there's an electronic control which is generating the waveforms, the DF and the compensation voltage fields to operate the instrument. Now, everything I'm going to talk about in my presentation this morning, all the results I'm going to talk about have been measured on this miniaturized chip-based system. But we have both systems in our laboratory. We haven't done any head-to-head comparisons between the two. Life is too short for that. But we have done some measurements on both instruments. And I think the point I would make is that some of the general issues and points I'm making about what FAIMS might be able to do for you and do for us are general to these two electrode geometries and indeed other configurations as well, although there are individual differences between the various different devices. So I was asked if I could look at a variety of different pharmaceutical-related things by Alex in the presentation today. And I wanted to start really by making a general point that, like drift tube systems, but if we've got an ion mobility device of some sort and a mass spectrometer, then we can look at the working point of an ion, which has been separated by our mobility dimension and our mass to charge ratio dimension. So in the case of drift tube systems, we would be plotting mass to charge against the ion drift time along here, as we saw in the previous presentations. In this configuration, we're plotting our mass to charge against the compensation voltage or compensation field against this, which is separated. And here's a variety of different sort of test compounds that we've used, pharmaceutical related and others, just to illustrate the fact that each of these has a point in the compensation field mass to charge space. So caffeine, proteinated caffeine, for example, A here, sits at this point in the system. One important thing about the FAIMS separations is that the separation of the ions and its relationship to mass is a bit different from that in drift tube systems. In drift tube systems, as you increase the mass, you tend to increase the size and collision cross-section of an ion, and therefore you tend to increase the drift time. So you tend to get sort of diagonal swooshes of ions going up in this direction, very common in the drift tube devices. In FAIMS, that doesn't hold at all. We're talking about differential mobility. It's a different separation process. So let's look, for example, ion A, which is proteinated caffeine, D, which is protonated MRFA peptide, and E, which is protonated reserpine in there. And you can see that although mass to charge increases along here, there's no simple relationship between mass to charge and compensation voltage. So the orthogonality of the separation between the FAIMS and the mass to charge separation can be greater in FAIMS devices than in drift tube devices. Okay, so what I've done is I've tried to set in the remaining 20 or 25 minutes or so that I've got some examples of applications of FAIMS to pharmaceutical and to bioanalysis from our laboratory. And I've just selected, it's a snapshot really of the work that we and others have done. Just tried to pick out a few examples which I think illustrate some of the essential and interesting features and the potential that FAIMS has. And the first one of those is looking at isobaric and isomeric ions, things that are problematic by mass spectrometry. We've seen in the earlier presentations have potential by ion mobility spectrometry techniques. We've already looked at isomeric separations by drift tubes, and you can separate isomers very well by FAIMS as well. I wanted to concentrate on an example looking at isobaric species. And the example that I've chosen are these two compounds here, trimethylaniline and N,N-dimethyltoluidine. And I've selected those for two reasons. The first is these are, or the substituted anilines are potentially genotoxic impurities in active pharmaceutical ingredients, and so their monitoring and detection at levels around about the part per million level is required. The second reason why they're of interest to us is because they're isobaric with each other. They don't separate by single-stage mass spectrometry, and in fact you can't resolve them even by tandem mass spectrometry. So if you want to carry out the separation, you've got to do some separation technique, and GC and LC are fine, but they both take time. What we wanted to know is if we could use a FAIMS separation to resolve them. And so if we put these and electrospray them into our FAIMS-TOF mass spectrometer, then we can monitor the M/Z156 because there are isobaric ions in there, and we see that as we scan the compensation field along here, that we can in fact resolve these two components to each other. This is the natural intensity abundance for equimolar amounts of these two compounds. So we're able, if we select the appropriate compensation field, to in principle transmit selectively one of those components in the presence of the other. For example, if we go here to around about 1.5, 1.6 townsends in our compensation field, we should be able to transmit, or can transmit, the NN dimethyl toluene selectively in the presence of the aniline species. So we have a separation which is effectively instantaneous. The time of transmission through the device is on the microsecond scale, so it's an instantaneous separation of these two species. And we've incorporated this into a rapid screening process for these particular compounds, which based on thermal desorption. This was mentioned in the previous presentation, that we can use thermal desorption of volatile species in order to extract them from their matrix. So in this particular case, what we're doing is we take an active pharmaceutical ingredient, which may or may not have one of these PGIs present. We place it in a thermal desorption tube, and we thermally desorb it at a temperature which will remove the volatile aromatic amines, but will not desorb the basic active pharmaceutical ingredient, which will remain behind on the tube. So there's no sample preparation except to put the sample in the tube, warm it gently so that we can take off the aniline and dimethyltoluidine components. We've now got those in the vapor phase, so we need to ionize them. We do that by a technique called extractive electrospray, where the vapor of the dimethyltoluidine, in this case, picks up a proton from an electrospray to ionize itself in an electrospray source of the mass spectrometer. It's now ionized, it's protonated. We can then carry out a FAIMS selection at 1.5 Townsend and dispersion field of 230 Townsend in there, which is going to selectively transmit the NN dimethyltoluidine, and we detect it as an ion MOZ136 in our mass spectrometer. And on the right-hand side, we can see the selected ion response of an ion that's been selected on the basis of its FAIMS compensation field and of its mass to charge, and we can see a nice sharp desorption profile along here, and this desorption profile is at the 1 ppm, the threshold level for the detection of a PGI in an active pharmaceutical ingredient. And the time scale for this, if you can't read it, 1.2 minutes at the center of the peak along there. So it's a very rapid direct screening method for PGIs, and it's made possible by the FAIMS separation of these isobaric species. The next example I'd like to talk about, and I think it's really important in terms of these separations, is about removing what I call the sample complexity, the chemical noise from a sample. And FAIMS is very good at this. We've got quite a lot of examples of these sort of processes. I've chosen a couple to talk about today, and the first one of those relates to a pharmaceutical intermediate, a potential intermediate, HOPB, in the presence of an excipient, which is kindly defined by our last presenter, an excipient polyethylene glycol, a very common excipient in pharmaceutical formulations. If you put these together, these are not actually isobaric, but the masses are very close indeed. 327.2013 for the N7 ligament of PEG, and 327.1955 for HOPB. You can separate these by mass spectrometry, but you do need a resolution in excess of 100,000. So you need a very high resolution device, way beyond the scope of the TOF instrument we're using here. So if you mix together a mixture of these two in the sort of ranges you would get in a formulation, in this case we're going to mix together 40 times as much PEG as HOPB. You put that into your mass spectrometer without FAIMS, then what you see is a horrible mixture, a spectrum, which mostly consists of polyethylene glycol excipients in there, and there's one peak along here, M/Z327, which is a mixture of the PEG and the HOPB. And if you look at the accurate mass of that, it's miles away from what we'd expect to get for the HOPB, because you're looking at the average mass of that and the PEG oligmer. So you can't resolve the two under these conditions. However, if you look at the FAIMS compensation voltage spectrum, or field spectrum, of these two compounds, we see that they are readily separated by FAIMS again, and we can select the HOBB and transmit that whilst discriminating against the PEG excipients in the system here. So we're looking at something around about sort of 0.5 or 0.6 volts on the compensation voltage scale. We should be able to transmit the HOPB. And I wouldn't be using this example if that wasn't, of course, the case. So this is the spectrum after the FAIMS selection. You can see we've suppressed all that background sort of chemical noise that we don't want from our excipient, the polyethylene glycols, and the HOPB is now the base peak, and the mass measurement on that peak is correct for HOPB at 2.7 ppm. So we're able to take a complicated mixture and extract out the component we want by reducing chemical noise. Now, I guess you may be saying, okay, that's fine. It's not really a terribly complicated mixture, and that's certainly true. So we've pushed this a little bit further, trying to move to more complicated matrices and the presence of analytes at very low concentrations in those matrices. The example I want to show on that is the UHPLC FAIMS-MS analysis and negative ion mode of the ibuprofen-acyl glucuronide metabolite in human urine. Setting up this analysis, we used a UPLC method in which we tried to reduce as far as possible the retention time for our IAG metabolite. And so we've pushed that as short as we possibly can, commensurate with it being retained on the column, allowing the non-retained components and weaker retained components to wash off the column before the elution of the IAG peak along here. The downside to that process is that even using quite a narrow mass window in our selective ion monitoring, 0.02 either side of M/Z381, we still get interfering species from the complex human urine matrix in there, and that makes quantitation difficult. We've tried doing the obvious thing. We've got high-resolution mass spectrometry. All you do is reduce the window over which you look and narrow it down. So we've narrowed it down from 50 ppm to 10 to 20 ppm, and it makes absolutely no difference at all to discrimination against the background interferences. They're very close in mass, so that doesn't work. You can, of course, change the liquid chromatography in it, and you can extend that. You can pull this peak out, and that will work fine, no problem at all. But, of course, that's at the cost of the cycle time for the analysis and the speed at which you can carry out your screening. So we wondered if FAIMS might be able to help that. And if you look at the FAIMS spectrum of IAG along here, we see that it's transmitted at around about 2 or 2.2 Townsend along here. So we should be able to selectively transmit IAG and discriminate against other components. Interestingly, also against ibuprofen in there, although that is separated chromatographically, we could in principle infuse the two together and separate the metabolite from the parent compound. But in this particular case, we've just selected the parent compound, and you can see that all of this background noise, which is associated with the peak, basically disappears, and we get a nice clean trace out of it, and we get all the advantages of the short retention time. We've looked quantitative at this system in some detail because we wanted to know quantitatively how it behaved. And the good news is that when we use the FAIMS separation, because we're suppressing that background chemical noise, there are a number of advantages. First of all, we improve the limit of quantitation because we've reduced the background noise. We can increase the linear dynamic range because the top end of the range is the same, but we've reduced the bottom end of the linear dynamic range. And because we're reducing noise, we get improved precision for the measurement. We're just not trying to measure our signal against a noisy background in there. So the potential for quantitative measurements using FAIMS does seem pretty good. And there seems to be a general case, we would say, of reduction of background matrix interference when you apply FAIMS to your system. I've not had time to share the data here today, or perhaps if I knew I was going to get 10 minutes more, I would have included the data. But we've also explored the quantitative determination of a peptide inside a complex matrix such as human plasma and get in preliminary data good quantitative measurements in that. So FAIMS is a good quantitative technique coupled with mass spectrometry and coupled with mass spectrometry and HPLC. The next example I'd like to deal with deals with charge state and conformer separations. And there we've seen this morning from the drift tube techniques that you can separate charge states by ion mobility spectrometry, and FAIMS is no exception to that. So I'd like to show an example of where in which we can do that. An example I've chosen is bradykinin, which if you electrospray it normally, you're going to see both a singly charged ion at M over Z 1060 and a doubly charged ion at M over Z 531. And in the inset in this slide, you'll see that we have the compensation field separation of these two ions. And whilst there's a fair bit of overlap between the two, I think you can see that if we select appropriate portions of the FAIMS spectrum, for example down here or up here, we should be able to transmit selectively the singly or the doubly charged ion. In this case, we can select, for example, a compensation field somewhere up around about 3.5, 3.6 volts along here. We should be able to transmit the doubly charged ion selectively, and that is indeed exactly what happens. We quench the singly charged signal here. Alternatively, we could have chosen a singly charged ion, and again in data which I didn't include in my presentation, we've shown in published data in its publication Analytical Chemistry down here, the first one of these two, that if you look at the singly charged ions of peptides, they tend to have a very narrow range of transmission in the FAIMS spectrum. So if you go to some of this region out here, around about 1 volt on the compensation scale, you can transmit preferentially singly charged ions and suppress all doubly charged ions. So if you've got an electrospectrum of a series of peptides, which is a mixture of singly and doubly charged ions in there, you can select and transmit preferentially the singly charged ones. In other words, you can generate a spectrum that's a bit like the peptide mass fingerprint of singly charged ions you would get if you did a Moldy experiment. So from the same electrospray data, you can obtain your peptide mass fingerprint and search that against database, or you could go in and select a particular doubly charged ion for, say, tandem mass spectrometry and identification purposes. All in the same run and all within a very short period of time. The other point I just want to make about this is you may be saying to yourself, blimey, this peak shape here looks pretty rubbish for a single component, and it does look pretty rubbish, but the reason why it looks like that is that it's not one single component. Bradykinin and doubly charged ion, singly charged ion, have a number of conformers. From other work we know there's at least 3 or 4 conformers of bradykinin, and that's basically what we're seeing here. We're seeing partial resolution of conformers of bradykinin by the technique. And this works for other peptides and proteins as well. This just quickly shows the ubiquitin, and for the 6th charged ion of ubiquitin, you can see that there's clearly a complex composite peak here, which is associated with different conformers. Now, Alex's presentation in a little while, he's going to talk a lot more about high-resolution separations of conformers in these systems. So I'm going to say no more about it now. You'll learn more from the master in a little while. Final part of my talk, what I'd like to do is to discuss how we can continue to enhance our separations. We've shown that we can get greater selectivity and isomer and isobaric separations using FAIMS separations when we combine the field asymmetric waveform separation according to differential mobility with mass to charge in our mass spectrometer. But we've been working on approaches which will enhance even further the selectivity of these techniques. And the principal one which I want to talk about today is called, we've abbreviated as FISCID, which is FAIMS Ion Selection CID mass spectrometry. And it works a bit like this. We know that if we take ions from a source, an electrospray source, we can use the FAIMS to pre-select ions of a particular compensation field or compensation voltage in there. So we can selectively transmit those ions through into the mass spectrometer. But rather than allow them to pass straight into the mass spectrometer to carry out the mass to charge analysis on those ions, in all atmospheric pressure mass spectrometer interfaces, it's possible to induce what's sometimes called in-source collision-induced dissociation, which occurs in the intermediate pressure region between the atmospheric pressure ion source and the high vacuum of the mass spectrometer. So that's very easy to do in any single-stage mass spectrometer. So what we're doing here then is selecting ions according to their FAIMS submission. We're carrying out in-source collision-induced dissociation on that selected FAIMS on, and then we can carry out a mass analysis of any residual precursor which is selected, and of course the fragment ions produced by collision-induced dissociation in the interface. So FISCID. Okay, let me just show you how this works by going back to that example of the HOPB and PEG that I showed you a little earlier on. If you remember, HOPB and PEG are overlapping, so there's this unresolved peak along here. And so in mass spectrometry, in the absence of any FAIMS separation, we have a complicated mass spectrum, and if you pass that through the interface into the mass complex sets of ions, formed the electric spray source, as you pass that through the interface into the mass spectrometry, if you undergo collision-induced dissociation, all of those ions are going to fragment, and you end up with a very complicated product ion spectrum in there. And so even in this region down here, which I'm about to show you, you end up with quite a lot of complex species in here when you do in-source collision-induced dissociation mass spectrometry without any FAIMS separation. And the HOPB fragments, which should be present in here, are very strongly suppressed and in the background. However, if we carry out that FAIMS separation first of all, remember I showed you this before, this is the protonated HOPB, separated at the appropriate compensation field by FAIMS. We pass that through and undergo collision-induced dissociation on that species, and under those circumstances, we end up with enhancement of the HOPB fragments and suppression of the PEG background. So we can see those coming up. So the PEG has now disappeared, it's back in the background noise, and we can pick up these fragments here. So we have the potential for enhancing the spectral quality so that we can confirm the presence of HOPB from the basis of the precursor ion and the characteristic fragments of HOPB. And not only can we use this for identification purposes, we can enhance the quantitative analysis of these compounds because we added another selection criteria. As in tandem mass spectrometry, instead of having selection of mass charge ratio, CID, and then mass charge ratio selection, here we've got FAIMS, collision-induced dissociation, and mass charge ratio. So an ion has to have the correct FAIMS transmission characteristic, and it has to produce fragments the right mass charge ratio in order to be detected, enhancing selectivity. Now, I guess you may be saying that's a simple mixture of that, but let's go to something which is a mixture of peptides. Here we've got the bradykinin in the game, but not on its own this time. It's a mixture of other peptides. But we know that if we apply FAIMS, we should be able to isolate the bradykinin doubly charged ion by the selection of the appropriate compensation field or voltage. So we can isolate that. We can then pass that through the interface of the mass spectrometer and subject it to collision-induced dissociation, and then look at the fragments that are produced by our time-of-flight mass spectrometer. And when you do that, you see all of the typical B and Y fragments which are associated with a low energy CID of bradykinin, and clearly we can use that to identify the bradykinin compound, although it was in presence of a number of the peptides. Of course, you're probably saying to yourself, that's a pretty simple sort of mixture. What about trying something more complicated? So we decided to really push the boat out on this and try some experiments using tryptic digest of depleted human plasma. So if you do the LCMS on depleted human plasma of tryptic digest, you end up with this extremely complicated chromatogram as a result of the many, many tens of thousands of peptides produced by the tryptic digestion process of the proteins in the plasma. And even if you go to one particular retention time at 3.5 minutes, we can see that even there are several peptides, here at least 3 identified, mass charge 480, 707, and 546, which are co-eluting at that particular moment. And they're not the only peptides co-eluting at that particular retention time. So if we look at a mass spectrum of this, even choosing a point where we think we might be transmitting at the 480, we end up with a mass spectrum which contains a variety of peptide species and other artifacts in the spectrum at that particular point. But if we use the FAIMS selection at the point, we should be able to enhance the transmission of one particular peptide, in this case 480.8. We've lost the higher mass peptides which are also present, and we've reduced a lot of the noise down here at the lower levels, partly because FAIMS generally reduces chemical noise, but also is discriminating against these species at lower mass. What happens if we try these two experiments but with collision-induced dissociation? Well, if we have no FAIMS selection on there, we end up with a very complicated spectrum along here, which if you put it into a search engine to identify the protein, finds no matches at all. It's just overlapping peptides which can't be identified. If we put the data from the FAIMS pre-selection in at the bottom, then we actually get a hit and are able to identify the component. Now, those of you who are eagle-eyed here today, or those of you who are watching it in your webcast and you're zooming in on this particular slide, will notice that the actual protein identified here from the peptide MZ480 is actually human serum albumin. And you'll be saying to yourself, well, hang on just a minute, that's about 60% of human plasma. This doesn't sound a very challenging task, but it's not quite as bad as that. Critical word here is depleted human plasma. We've been working on depletion processes to extract out the major and high molecular weight proteins in the system, and the technique which used here, which we published in Rapid Communications a few years ago now, about 3 years ago now, is extremely efficient at depleting some of the major housekeeping proteins, in particular human serum albumin. In fact, it depletes at least 99.6% of all the proteins in the plasma sample. So human serum albumin in this particular trip to digest of what was left out of that is quite a minor component of the total mixture. So despite our very best efforts to get rid of the human serum albumin, it's still there, and we're able to pick it out in this particular analysis. So the Fiskid technique has the possibility of enhancing our FAIMS separation over and above the simple FAIMS mass spec combination. Okay, so it's just finished in the last few minutes available to me. What are my conclusions, or our conclusions on our experience with FAIMS, and particularly with the microscale chip-based FAIMS? Well, first of all, we can carry out these orthogonal separations based upon differential mobility and mass to charge, and if you use chromatography on retention as well. And so effectively we can enhance our analytical space. We can improve the peak capacity by adding FAIMS separations to mass spectrometry, or LC and GCMS. We can carry out we carry out isobaric separations and isomeric separations. I'm not showing isomers, but there are a number of examples in the literature and examples from our laboratory, which I haven't had time to talk about today. We can carry out charge states and conformal separations on species. But I think one of the most interesting things about the FAIMS is that we can reduce sample complexity. We can do that and improve the signal-to-noise and discrimination of our target ions from background chemical noise by suppressing chemical noise. And we can do that, and we can use that to enhance our quantitative performance and our limited dynamic range in these systems. And perhaps the most interesting of all, as mentioned earlier, one of the most important characteristic of FAIMS and ion mobility spectrometry, as far as I'm concerned, is the same device, the same hardware, can do everything from tiny little ions up to great protein assemblies without any significant change in the operation of the systems. So we have a wide range of structural, qualitative and quantitative applications available to us. Well, I'd just like to finish by pointing out, as I always do in these things, that I don't do any of this stuff at all. And of course, my research group will be the very first to point out that I don't do any of this stuff as well. So I'd like to acknowledge my current research group, collaborators Jim Reynolds, Steve Christie, and Paul Thomas, who's with us here today and is speaking at one of the ion mobility sessions tomorrow. To our collaborators on this work with the chip-based FAIMS system, and to our funders. And if, I guess, out of what I've shown you today and the various different examples, I've caused you to have just one single thought, and that is, what might FAIMS do to me, or for me, then I think I've done my job today. Thank you.
Thank you, Professor Creaser. Question, please. Thanks, very good talk. Can we go back to this slide of the
Conformal separation, yes.
Well,
okay, yeah. Yeah, Alex is going to elucidate this in much more detail in a moment, I think, aren't you, shortly? Yes, but if this particular species, the doubly charged species, from other studies using drift tube and other techniques, it's known that this species is not a single conformer. It's at least 3, and I think probably 4 discrete conformers. And they have different collision cross-section, but they also have different differential mobility because of their size and shape. The way in which they will interact is different in FAIMS. And so what we're seeing here are 3 partially resolved conformers. If there's a 4th one, it's hidden underneath that species. Interestingly, if you run this by drift tube mass spectrometry, you do see a similar profile. And also, actually, if you run it on the cylindrical geometry device, which we've done as well, you also get a very similar profile as a result of partial separation of the conformers. So I've just missed it. On the mass spectrum? Oh, well, that's a separate thing. What we've done here was we simply selected this particular conformer. In fact, we could, in principle, select this conformer or that one. We select that particular conformer at this particular value, and that's how we were able to extract the doubly charged ion in the presence of the singly charged ion. Yes, in fact, well, we're working at the moment on looking at this where we might be able to either situations where you can transmit selectively one conformer, which maybe Alex is talking about, so that you can do chemistry on a particular conformer, or to collapse them all down to a single peak so that you remove that partial separation, and you can do both of those.
Okay, let's look at the question, please. With respect to this slide on the dimethyl amine, you had indicated that thermal absorption ESI. It seems to me that was like a chemical ionization. Can you explain that?
Yeah, okay, this is what you might call extractive electrospray technique introduced by Renato Zanobi. So you can go and look at his analytical chemistry papers on that. What happens is that you have an electrospray plume which has your normal electrolyte in it. So in our case it would have methanol water with 1% formic acid, 0.1% formic acid in there, and you bring in a sample stream, which could be a liquid, but in this case is a vapor, into that. So the vapor interacts with the electrospray. The mechanism is not entirely clear, but it must associate with a droplet in the electrospray, and it can pick up a proton from that and be dissolved out in the vapor phase like a normal electrospray spectrum. And so you get charge transfer from the electrospray droplet to your gas phase molecule.
It sounds more like chemical ionization, by generating ion from an electrospray source.
Well, that's a matter of uncertainty. What we don't know is, are you dissolving your molecule inside the droplet and then getting normal electrospray, or whether it's some more complicated surface-related process on it. It's difficult to distinguish between the two of those. But it works. That's the main thing. Yes.
Do you ever observe the 3+ charge state kind of reason I'm asking that?
Yeah.
Recent papers, David Clever has published one high resolution of 3 or 4 major charge states, so 3 or 4 major conformations, and 2 really minor.
Yeah.
Just wondering what
Kid.
distribution you see on papers is
No,
across 3 charge states.
That's interesting, because in this case we did not see the triply charged species. But, sorry?
Can you repeat the question?
Oh, so yes, the question was, in the bradykinin, do we see a triply charged ion as well as the doubly and the singly charged ions? Because there seems to be some question about whether that's transmitted effectively in ion mobility.
Mainly wondering about how, if you were to see it, the confirmations that you observe on FAIMS, how similar would they be to the ones that...
Yeah. Well, the answer in these experiments, we've not seen the triply charged one. Interesting, maybe in drift tube you can see it quite clearly, and we've transmitted it. With FAIMS, we've not seen it. We've not really bothered to look for it very much, so I don't know whether it's there or not, and we've certainly not looked at any conformer separation associated with it. Okay. Ion transmission, improvements in ion transmission, improvement in the ion transmission through the FAIMS device was the principal driving force behind that. Yeah, but the of course the downside is that the field applied is less, unfortunately. So it's a compromise between the two. Certainly, what Ekin's referring to is the earlier prototype devices, chip-based devices, were 35 micron gap. That's been increased to 100 micron gap in order to prove transmission through the FAIMS device, which was pretty poor, I have to say, with the 35 micron, and is significantly better with 100 micron.
Okay, is there any one last question? Okay, then let's thank